It's in the nature of science that it is a building of a shared knowing over time, and it modifies itself as we increase and improve our understanding of the natural world. The tools we use to do this become more refined over time, such as, for example, a measure of linear length, which is connected, of course, to volume, and if we add time, connected to speed. And time and speed and volume become fundamental to so much of our science. How did we get here to where we are in the present? Having a shared global universal concept of linear measurement, a meter, that is conserved and consistent. That is, that every time we use it, we're going to get pretty much the same amount. It has exquisite sensitivity because we have used a decimalisation to break it down into tenths and tenths and tenths, or to multiply it up by 10 by 10 by 10. And so we are capable also of extreme ranging. So we can measure the very minute, the nano size of things, as Linda mentioned in GTV 110, or the distances across galaxies and space itself. How did we get here? We're going to pull back the curtains on time. If we pull back and look way back in time, a long time ago, we find that local communities, small groups of humans, had customary units that were consistent and conserved. You could use the length of your joint of your thumb, the length of your digit, or the size of your hand. And each time you came back to them, within reasonable variation, they could be relied on. And each time you used your hand, it will be giving a similar reading, consistent and conserved. But then, over time, as we pull the time back further, we find that these were formalised by large civilizations, where it was important to record and to share over greater distances and with more people these ideas of measurement. So the forearm and the hand and digit became formalised, and an example would be the cubit, which was the length from the tips of your fingers to your elbow, and was equivalent to roughly 6 palms plus 4 digits. Militarization of large civilizations such as the Romans started to use the foot, the stride, and the march. The march gave us the mile. 2.5 miles per hour was the average speed of a centurion marching. 8 hours marching, 20 miles. And that could be broken down into smaller fractions to give smaller distances. Still customary, still with consistency and conserved, but as you can imagine, full of variation. It wasn't until in more recent time, when we had the development of decimalisation, that enabled us to have a more formalised system that was easier to manage and convert from one system to another. And then a global reference, which was easier to become more universal across more people. And this was 1/10,000,000th of the distance from the equator to the North Pole, going through a meridian in Paris. That became the definition of the meter. An artifact was needed so that this could be referred to consistently, because it wasn't easy to go out and get a reference to this all the time. And an iron bar became the artifact, which was the standard reference. Of course, it wasn't always so consistent and conserved because of thermal expansion and contraction of iron, and it was improved more recently by making the bar an alloy of platinum and iridium, which had a far smaller thermal expansion coefficient, but still needed that. This was still referenced back to that global measure. But then, in more recent times, when we had better instrumentation for more precise measurements, the definition became related to light. The wavelengths of orange-red light from the krypton 86 atom was a reference standard. The number of wavelengths, that precise number of wavelengths, became a meter length. This allowed for more precision and was highly consistent and highly conserved. This again was updated and improved, and it was the distance that light travels in a vacuum in a time of this number of seconds, a tiny fraction of a second, where the time is precisely and accurately measured by the vibration of the cesium atom. This again is highly conserved, highly consistent, and allows for remarkable precision. And this is where we are now today. So that meter rule that we have, that meter length that gives us volume and speed and a linear measurement, is defined by this standard and is calibrated against this, which allows for exquisite sensitivity, down to the nano size, as we mentioned before, and extreme range. And this allows us to explore further within the natural world that we exist and further beyond this natural world we exist. And our ocean world utilizes these all the time. Now, a whole lot of names could be placed here, individuals, but really it's a communal effort by many, many people working and thinking on this problem over eons of time that have reached this point. And it's probably not the end point. The characteristic of science, remember, is that the present is built on the shoulders of the past, and the knowledge building community works towards a greater universality and reliability of the data that we can share as shared knowledge. And that knowledge is distributed. No one person holds all the knowledge. No one artifact holds all the knowledge. It is the combination of all artifacts and all people that pull together to make that distributed cognition, that spread knowing, that science becomes. Well, we've got our system of linear measurement with our standardisation, which is conserved and consistent. How does that relate to precision and accuracy? Well, here's another little game you can play with your bubble. You can play this builder's game where you just get a meter tape and you try and pull it out to get it close to a meter as you possibly can. And then have a look and see what you got. And I've got 1 meter, 109 centimeters. Well, the actual standard of 1 meter is pretty conserved and consistent, but my use of it has an inaccuracy. That was a positive bias. All right. How precise am I? How often am I going to get close to that? No, this time I'm 111. And again, 110. I'm consistently got a bias, so I'm not that accurate, but I'm reasonably precise. 109, 111, 110, I'm hitting it pretty much the same sort of mark. So basically, the standardization doesn't affect the precision and the accuracy of your use, except that the precision of its definition, the consistency and dependability of it, its conservative nature, means that it allows for greater precision if you do use it carefully and accurately.